Okay, so we now know how does a ideal gas operate macroscopically. So in our derivation of PV equals NKT, we assumed that we had this box that we could see, and so it was a macroscopic box that contained some air molecules. Now it turns out that there is another way of analyzing a gas, but this time instead of thinking about its macroscopic properties such as pressure and volume, this time we're going to look at its microscopic properties. And we're also going to need to use mathematical concepts from statistics in order to do it. And so this is going to be called kinetic theory. And so this is another way of analyzing the way a gas operates. Now we're not going to be using any statistics in here, but I just wanted to show you the postulates of kinetic theory and then some of its applications. So postulate number one is you are going to be using a large number of particles, which is no problem whatsoever because we just found out that in chemistry they're talking about moles, which is 10 to the 23rd atoms or molecules of a gas. So whenever we're talking about kinetic theory, we are thinking about huge numbers of things that are interacting with each other. The second thing is that the distance between the particles is going to be much larger than the diameter of the particles. So here, for example, is a particle of gas, and let's say that it's got a certain radius r, so it's got a certain radius, and then over here is another one, and so it also has a certain radius r. So one of the postulates is going to be that these things are going to be very small compared to the distance between them. And again, think about the size of an atom. So the size of an atom is like 10 to the negative 10th meters in diameter. It's teeny tiny. And now let's think about the distance between gas particles in the air around you. Well, that's something like in centimeters, so that the air molecules are separated by a distance of a few centimeters in the room. And so this number here is very small in comparison to a centimeter. So therefore, postulate number two is necessary when we're talking about kinetic theory. And then the third postulate says the interactions are only elastic collisions. So when we talked about momentum, we said that there were two different kinds of collisions, elastic and inelastic. So in an elastic collision, imagine you got a steel ball and you drop it on the ground. If that ball hit the ground and then bounced up exactly to the same height, then that would be an elastic collision. No energy would have been lost in the collision. So no energy would have been turned into heat. Now, on the other hand, imagine you got a piece of Play-Doh, clay, and you drop the clay on the ground. Well, it doesn't bounce. It just kind of hits and then sticks to the floor. So that would be a totally inelastic collision. So we're going to assume that these atoms are going to be constantly bumping into each other in the gas, but when they bump into each other, they do not lose any energy. So they're going to bounce and then come apart when that happens. So those are going to be totally elastic collisions. And then postulate number 4 says that the average kinetic energy of the particles is going to depend on its temperature. So we already knew that. So earlier we mentioned that heat, Q, is proportional to the temperature T. So that the higher the temperature of a gas, the more energy the gas is going to contain? Well, there are different kinds of kinetic energy. So let's look at the first one there, where you've got these two molecules, and each molecule has a mass m, and they're both moving. So maybe there's a chain or something that's connecting them, and so they're moving back and forth with a certain speed v. So the kinetic energy is 1/2 mv squared. And then that, it turns out, is that energy is proportional. So energy is proportional to the temperature, and it's going to be equal to 3/2 kT. Now, do you remember the K? So the K is this one up here, which is the same as this K right here. So the average energy of those molecules is going to be equal to 3/2 kT. And then if you want to know the total energy of all of those molecules moving around, then multiply that by N, capital N. So then it would be capital N, 3/2 kT, would then be the total kinetic energy of molecules when they're moving around. Now you might be wondering, where's the 3 coming from? So it's 3/2 kT. That 3 is because something can be moving in this direction, but could it be moving this way? And also, couldn't it be moving this way? So there are 3 dimensions that this thing could have as it's moving around. So that's why it's got 3/2 kT in there. But that's not the only thing that some molecules can do. So some molecules can be rotating, like a dumbbell. And in a previous lesson, we talked about the kinetic energy of rotation depended on the moment of inertia, I, and then how fast is it spinning, and then that was called the rotational speed, omega. So that's that W looking thing. Now it's not a W, it's a Greek letter, omega, and so the kinetic energy of something when it's rotating around and around is 1/2 I omega squared, and then that energy is going to be equal to just kT, not 3/2, but just ordinary kT. Now if you want to learn why isn't it the same number in front, then take a physics class and you can learn more about that. It's not that difficult, but it's just not that important. Then a molecule can sometimes be vibrating. So think about water. So water is H2O. So that's the formula for water, H2O, which means it's got an oxygen and then it's got hydrogens on it. Now, if you might be wondering, well, why is it shaped like this? Well, it has to do with chemistry again. It has a certain shape to it, so it's called the Mickey Mouse molecule. And you can think of the electrical forces that are holding the oxygen and the hydrogens together as being like springs. So you can think of it vibrating like this. But it could also be vibrating like this. See what my fingers are doing? So there are different kinds of vibrations that a molecule can have. And so in a previous lesson, we talked about the energy of vibration, the energy of a spring. And it was 1/2 the spring constant, which was the stiffness of the spring, and then multiplied by the distance that it's stretching, squared, and then that energy is related to its temperature by kT. So these are different things that a molecule can do. Now if it's an atom can really only be moving sideways and in and out. So an atom doesn't really have a whole lot of energy when it's spinning, and of course an atom can't stretch because it needs to have a partner in order to do it. So it kind of depends on what are the gases in the system as to which of these different kinds of formulas that you use. But the point is, okay, let's summarize here, that the average kinetic energy of molecules is going to be related to its temperature. So the higher the temperature of a gas, the more energy the gas is going to have. All right, let's take a break. And when we come back, let's do an application of what we just talked about.